Okay, thanks, Hussein. Yep. Microphone's working, so that's good. So Hussein asked me to give a site update for CSCS. I think it's a few years since we've had one of these, so I'll run through a few things. Some of you may have already heard the information. Some of it may be new for you, but so if we just look at CSCS, what we are, there's our facility, the data center here at the back, and our office building at the front. So we were established in 1991 as part of ETH Zurich. They're a unit of ETH Zurich. And currently we have more than 90 motivated staff from roughly 15 different nations. So we're a pretty multicultural environment. Obviously I'm not Swiss, I'm originally from New Zealand. And we now have a division in Zurich that's working on scientific software and libraries, so-called SSL unit that we have up there now, run by Joost van der Wanderley from CP2K fame. Our mission is to develop and operate the key supercomputing capabilities that are required to solve important problems for science and or society. And our communications team say that we are driving innovation and computational research within Switzerland, and I think that's probably fair. So we lead the national strategy for high-performance computing and networking, the so-called HPCN, and that was passed by Swiss Parliament in 2009. And those of you that know CSCS from the past, you'll know that we've had quite a lot of growth in the time that Thomas Scholtes has been our director. I think when he started in 2008, we had roughly 30 people, so we've had pretty sustained growth in the centre in the time that Thomas has been in charge. So we have a dedicated user laboratory for supercomputing since 2011, and this research infrastructure is hosted and funded at the ETH domain level on a programmatic basis. We have something like 1,000 users and roughly 200 projects. And we're also winner of Swiss ICT Innovation Award. This is kind of old news. Some of you may or may not have heard about it. In 2016, I think it was, we won the Swiss ICT Innovation Award for the work that we did with Medio Swiss for the Cosmo refactoring and the building of a dedicated HPC numerical weather prediction appliance for that code to run on, so all GPU based. And they were the first Meteo site in the world to use GPUs in production, as far as I know. So a lot of good things happen at CSCS. We have a flexible facilities infrastructure. We're very lucky with the building that we have. Some of you may have seen it. If you look at the cross-section of the buildings that I showed you in the first slide, you see our office building here, but the really interesting bit for the IT nerds of us is this building here. So this is the machine room. Then we have this installation deck where we do the secondary distribution of power and cooling infrastructure. And then we have the basement, which is where all the primary distribution of the cooling and electricity supply takes place. So we're currently set up for 12 megawatts, and we can upgrade to 25 megawatts. And we have this free cooling that we get from Lake Lugano, not far from here, just looking sort of in that direction, I think. Out to the lake is where these baskets are at minus 40 meters or thereabouts, and the water gets pumped up the river to our site, and we exchange the heat with it. Our PUE is currently around 1.2. Our flagship system, Pitsteint, is a hybrid heterogeneous system. So it's comprised of an XC40 partition and a hybrid XC50 partition. I'll just run through some of the details of the system. So obviously that's a picture of it there. So it was originally operational in 2013, but we expanded it and upgraded it since that time, made it a hybrid system, and then we upgraded it again in late 2016. So at the moment we have nearly 5,500 of these hybrid nodes with Xeons and P100s, And then on the same interconnect fabric, we have roughly 1,800 Broadwell nodes, dual socket Broadwell nodes on an Aries interconnect. Total system memory, I didn't rework this number. It's roughly, it's a bit more than this 520 terabytes of RAM. And the peak performance of the system is, the hybrid partition is a bit over 25 petaflops, multi-core partition, I think actually that number is a stale number, but it's up towards the 2 petaflops. The system has a measured impact performance of 19.6 petaflops roughly. And it's the most powerful petascale supercomputer in the top 10 of the Green 500. We're not as high up the list as we used to be, but we're still on in the top 10. And at our scale, I think there's only one other system on the list there. So we're very happy with this system. I'll just run through some evolution of the machine. So in the 2013 timeframe, you can see it was just a hybrid system, an XC30. There was no multi-core partition, so the things here in green are the things that we really added, apart from obviously upgrading the hardware itself to the newer GPUs and newer CPUs. So we added public IP routing to from the compute nodes to the CSCS network to make the compute nodes like peers on our network, and we moved to native SLURM, which was all made possible by this public IP routing. We moved away from the SLURM plus ALP solution, which we had been instrumental in engineering back in, I guess it would have been 2010 timeframe. So you can see a bit of the evolution of the system there. In the past, we had a 2.7 petabyte Synexion 1600 scratch file system. We augmented that with Synexion 3000. We have external GPFS on selected nodes. So there has been some evolution of the system in the time that we've had it. If we look a little bit more about that evolution, the functionality that we added to the system is really just to consolidate it as we view it as a consolidated HPC environment. So in the past, we were providing more traditional, shall we say, HPC environment, some scale-out computing, some visualization, some data analysis, but now we've augmented it with pre- and post-processing elements, data mover, this data warp technology from Cray, which is embedded SSDs inside the system, machine learning and deep learning frameworks, and support for Docker, which was described in detail by Alberto this morning. And we have a number of customers that are really peers in the system. They have contractual arrangements with us. They've bought into the system in some way. So we're servicing not just the user lab community in Switzerland, but also things, and because this is peer reviewed, right? To get access in the user lab, you go through an exhaustive, extensive, and very competitive allocation process. You have to apply for that. We have an arrangement with the University of Zurich and also with Paul Scherrer Institute, this Marvel project from EPFL. We also have some involvement with PRACE and with the Swiss Institute of Particle Physics. I'll talk a little bit more about that in subsequent slides. Need to move along a bit. So the ecosystem of the machine. We have our consolidated HPC environment. Of course, it doesn't do everything that we need. It has some scratch storage, but we have some site-wide, what used to be called GPFS. We have tape library, the usual things. We have a data center-wide IB and Ethernet network. We have some systems that are dedicated to some customers. The chip cluster, some of their functionality there is now being embedded in this consolidated machine. And we have some on-site cloud IaaS, so infrastructure as a service. So I want to just talk a little bit more about that now, because what I've told you up till now is really where CSCS has come from and what we currently are now. And just now we can talk about some of the visions we have for the future. So infrastructure as a service, what is it? I think we all probably know in the room, but I put this here for the sake of completeness. So you're delivering computer infrastructure on an outsourced basis to support enterprise operations. So the enterprise community has got a lot further ahead with this stuff than us HPC centers. We're playing catch up a little bit in some ways. But you provide hardware, storage servers, and network components, and also maybe some software. The key thing is it's all about service. So you have your infrastructure services at the bottom of this upside-down triangle, your platform and software as a service as you go up. If you're a platform provider, it's good for you because if you're here on the left as a platform provider, you have to provide the entire stack, physical hardware all the way up to the software, the applications. Infrastructure as a service means that you can outsource some of that stuff. So from a virtualization layer down to the actual physical hardware, the storage, the network, you can get someone else to do that. That someone else is us, CSCS, as an example. Then at the platform level, you can outsource even more, and then at the software level, you can outsource even more. It's, I think, a simple but powerful idea. So why use it? For us as an HPC center, it means that we can enable the hosting of domain-specific portals that are managed by external entities. So here is an example of one. I've tried to anonymize this a little way in some ways, but this is an actual example of a web service that we have running as part of a platform that we host for our European project. And what it means is that you can separate the concerns. You don't need to get involved with with all of this that powers the portal. You just provide the infrastructure layer, and then they take care of this, and the users come in and use that. It also means that dynamic provisioning can be made possible so long as these web services are somehow scalable. Then provisioning of this platform as the load increases can be done automatically. But there are some challenges, and the challenges are that you as an infrastructure provider, you now don't have much visibility of what happens inside these VMs for these web services, and so that can make troubleshooting a little bit more difficult. You have to have a good relationship with the platform provider. So OpenStack is an example of infrastructure as a service, and its architecture can be conveniently summarized in this diagram. Of course, the details are much more complex than this, but it's really software-defined compute, network, and storage all in one environment. So we decided to get involved with these technologies a couple of years ago, 18 months or so ago. So we put together this Pollak system. It's the first incarnation of generic cloud services that we offer as a production service to users. So it's an environment that has roughly 30 servers in it, new servers for controllers, directors, the compute. It has its own dedicated network. We've got roughly 30 terabytes of Ceph storage, and then we have some external Swift on GPFS, this guy down here, which was challenging for the consultant that we had involved with our team to set this system up. He hadn't seen this before, but Stefano, our storage expert, was pushing for this, and rightly so, in my opinion. So we have, it's deployed with this Red Hat OpenStack Platform 11 currently. And for those of you that know about OpenStack, you're on a 6-month cadence for upgrades of this, so it won't stay on this version for very long. It's been in production since last year. We faced some challenges to integrate it with our Kerberos and LDAP environment. There were some intricacies in our LDAP Kerberos environment that meant that the Keystone AAI within the OpenStack couldn't really interface to this, so we had to introduce Keycloak, otherwise known as Red Hat Single Sign-On, into the whole equation. That was also a learning curve for the guys. And we have some specific firewall rules configured for the internet service, internet-facing services that run on the system. And it's now hosting production platforms for third-party projects. We're adding more hardware as we go along, and we're augmenting the cloud offerings, but this is ongoing work which I won't mention in this presentation today. That'll be subject of a future presentation, I imagine. So, bringing things together, What we want is we want to have PITSDINT as a system that can provide similar services. You saw this morning from Alberto's presentation that Shifter is a technology that enables you to run Docker containers on an HPC system like PITSDINT. I won't go into the details again. Alberto did, I think, a great job with that. But the idea is you want a native GPU and MPI performance on our system. And we've actually found that it can improve parallel file system performance for some applications because you don't get the overhead of the metadata operations. So those were some unexpected benefits. But current use cases for this LHC on Cray, which is basically this chip, the Swiss particle physics community that are running in a Docker containerized environment on PITSDINT with a selection of nodes. And Alberto was asked a question this morning about what's the usage, and we currently, the guys tell me, we're roughly 5,000 container launches a day. It's mostly, I think, coming from LHC on Cray, but you know, this Docker plus Shifter thing is not a hypothetical thing. It's a real production environment that is getting quite a lot of push from here. We also have data analytics frameworks that need this containerized workflow, as well as some platforms that come to us from the Human Brain Project. This neurorobotics platform is an example of that. And others are coming, so watch this space if you're interested. So bringing this all together, and this is my last slide, which I think is good because I'm nearly out of time. So IaaS relies on REST APIs to offer services to platforms, and we collectively term these infrastructure services. I don't think we're the only ones to do that. OpenStack is an example of a way that you can do that. For PITSDINT, we need other mechanisms to provide these necessary infrastructure services, APIs, and work is underway in that area. Of course, bringing an HPC system like PITSDINT to this modern enterprise world of infrastructure as a service is not such an easy thing, as I'm sure you can all appreciate. But the benefits of IaaS also open the door for interactive supercomputing. We have some projects that we're in the process of signing that will offer these to end user communities. So there are many use cases that come from various user communities for this. There are some implications for policy changes, which also need to be managed as part of this whole transition. But this, of course, does not mean that we do away with our usual operations. Our user lab will remain our main core business. And these new services are a way to augment our capability, in our opinion at least, and open doors to new communities. So that's all I have. So I open the floor for questions if you have any.